Hello, everybody, and welcome to the Thursday lecture for week 7. So today we're going to talk about big primes and perfect numbers. So the motivation for this talk is essentially last week when we were doing cryptography, both in Diffie-Hellman and in RSA, I just said use big prime numbers. Like pick P and Q to be big prime numbers. And actually you have to stop and think whether big prime numbers even exist. For example, maybe there are only 1,000 prime numbers. So the fact that there are infinitely many prime numbers and thus arbitrarily large prime numbers is actually a fact that needs some justification. So that brings us to our first result of today, which is a theorem due to Euclid that says there are infinitely many prime numbers. So there are any number of ways you can prove this, but let me give the original argument. So suppose there aren't. So suppose there are only finitely many primes. So this is a proof by contradiction. I'm going to start by supposing there are only finitely many primes. And then we're just going to give them all names. So it'll be P1 through PK. Okay, so this would mean, if this were the case, this would mean every other number could be written as a product of these primes. Okay, but so far nothing we've done in the class would contradict this. I mean, this would just mean when we have unique factorization, only these K numbers showed up in the prime factorizations. Good, but so suppose there are only finitely many primes, and we have to get some contradiction. Okay, and so let me let n be the product of these prime numbers. So P1 times P2 all the way up to 2 times PK plus 1. Okay, so n is an integer. Good. Let me write up here, this is a complete list. Okay, so I form this integer n by multiplying together all the primes and then adding 1. And then n is an integer, so n has a prime factorization. So there is an I such that Pi divides n, right? Because n is a number, it has a prime factorization. It has a prime factorization, so if I only have these finitely many primes, so one of them must be a prime that divides n. Okay. But on the other hand, I mean, n is congruent to 1 mod Pi. Just from this equation, I mean, here, this product is divisible by Pi. When I sort of, this product becomes 0 when I look mod Pi. So I just get sort of n is congruent to 1 mod Pi. But on the other hand, so that's sort of coming from this expression. But since Pi divides n, this is saying n is congruent to 0 mod Pi. But 0 is not congruent to 1 mod Pi. So 0 can't be congruent to 1 mod any sort of positive, any integer greater than 1. But sort of prime number by definition is larger than 1. So this is the contradiction. So somehow I've assumed this fact. So I've assumed that there are only finitely many prime numbers. So then I created sort of some number n by multiplying together. I took some prime factor, which had to be one of these finitely many prime numbers. And from that, I sort of deduced that this had to be a number that's congruent 1 mod Pi and to 0 mod Pi. And so thus 1 and 0 are congruent to mod Pi. but that can't happen. So that means I must have assumed something that was not true to begin with. So this is the idea of proof by contradiction, is if you can assume something, then sort of show that that implies something that's already is not true, then the thing you assumed must have also been false. So that means this first thing we suppose, that there were only finally many primes, is false. Okay, so that's Euclid's proof that there are infinitely many prime numbers. Of course, there are different ways you can write this same proof, so it's sort of fun to try writing it sort of constructively instead. But good, that's good for now. So, and now we know RSA and Diffie-Hellman are going to work in the sense that you really can pick large prime numbers. Of course, finding large prime numbers is a different story altogether. And so for the rest of today, I just want to sort of talk about one fun topic related to large prime numbers. So this is going to be about perfect numbers and Mersenne primes. So here's a definition of a perfect number. So a positive integer n is called a perfect number if it is equal to the sum of its proper divisors. So in other words, in sort of mathematical notation, this means the sum over all of d over all divisors d of n, except sort of n itself, gives you n. So for example, 6 is a perfect number because the divisors of 6 are, the proper divisors of 6 are 3, 2, and 1. The proper divisors of 6 are 3, 2, and 1, and 6 is equal to 3 plus 2 plus 1. Good. So there's, and this is a simple definition. It doesn't look like it has anything to do with prime numbers, or big primes even, and somehow it does. It's kind of, and it's one of these sort of classic interesting statements about number theory. Like interesting things you can investigate in number theory. So going way back to the start of the class, the reason this condition is interesting is because it's mixing something about multiplication with something about addition. So here, the notion of a divisor, that's related to multiplication, but sort of then I'm adding up the divisors, that's sort of related to summation. So somehow this is an interesting mix of multiplication and addition, and that's why it gives you an interesting property to study. And there's this amazing theorem due to Euclid. No, not Euclid. Sorry, that was. There's this amazing theorem due to Euler that says an even number, n, is perfect if and only if you can write it in the following form. So we're going to write n as 2 to the L minus 1, so some power of 2, times the quantity 2 to the L minus 1. So you take a power of 2 and sort of the next, so you multiply a power of 2 times the next higher power of 2, subtract 1. And this is going to be perfect exactly if, so this next higher power minus 1, so this 2 to the L, then subtract 1, so this odd number 2 to the L minus 1, if this is a prime number. So every even number, every even perfect number can be written in this form with 2 to the L minus 1 a prime. And by sort of, and conversely, if you have some number L such that 2 to the L minus 1 is prime, then this number gives you an even perfect number. Okay, so for example, well, we saw 6 is a perfect number. And if you take little l to be 2, then, well, 2 squared minus 1 is 3. And that's a prime number. So it's sort of this is supposed to hold. And indeed it does. So 6 is equal to 2 to the 2 minus 1, or 2, times 2 squared minus 1. Good. On the other hand, so you could go up and you could do this with L equal to 3. And you'll get 2 cubed minus 1, so that's 7, that's prime. So this is supposed to give you then a perfect number. And indeed it does, it gives you 28. So if we sum up the divisors, they're 1, 2, 4, 7, 14. And if you add those up, you'll get 28. Good, so this is a way to produce perfect numbers, and it's related to or when this other quantity is a prime number. This doesn't work And this condition that 2 to the L minus 1 is prime will not always hold though. So if we go up to the next L, so we could take L equals 4. Well, if we look at 2 to the 4 minus 1, we get 15. That's not a prime number. And well, if you sort of write out this expression, you're going to get 120. And you can check 120 is not a perfect number. I didn't write it out here, but it's not so hard to just add up those divisors. Okay, so this is a pretty interesting result, but it gets more interesting. So this result of Euler's describes exactly the even numbers, the even perfect numbers. It's a completely open problem about whether there are odd perfect numbers. So we just don't know if there are any odd perfect numbers. We know there aren't any sort of in the realm where we can sort of run a computer search for them. So we know there are no odd numbers less than 10 to the 1500. So if you want to, or odd perfect numbers less than 10 to 1500. So if you want to try writing down an odd perfect number, you should sort of start with something with at least 1501 digits. Okay, but sort of even then you're not guaranteed to find anything. So I guess people sort of suspect that there are no odd perfect numbers, but really we just don't know. So this is sort of quite an interesting contrast compared to the even case. We have this very explicit description of what they look like. Well, that's sort of one of the charms of number theory is you can change a question a little bit and the answer can change a lot. Okay, but let's go back to this even condition. So important here was this condition that this 2 to the L minus 1 be prime. And so let's give those things a name. So a prime number of the form 2 to the L minus 1 is called a Mersenne prime. These are very special for more reasons than just sort of being connected to perfect numbers. There's an important observation we can make really quick about numbers like 2 to the L minus 1, which is that such a thing can only be prime if L itself is also prime. So the reason is if I sort of expand out, if I sort of have, if L is a composite number, so then I sort of can write like L is equal to A times B, then I sort of can always find a factorization of 2 to the AB minus 1 as 2 to the A minus 1 times 1 plus 2 to the A plus 2 to the 2A plus 2 to the 3A plus and so on, all the way up to 2 to the B minus 1 times A. So if you multiply these two together, you're going to get some telescoping sum, and you're just going to be left with sort of the minus 1 times 1. It's giving you this minus 1, and the 2 to the A times 2 to the B minus 1 times A. So together, that's giving you 2 to the B times A, or 2 to the AB. So these two combine to give this part, and then everything in the middle cancels. Like minus 1 times 2 to the A cancels with 2 to the A times 1. So minus 1 times 2 to the 2A cancels with 2 to the A times 2 to the A, and so on. And this already puts sort of another big restriction on sort of the existence of Mersenne primes and thus on the existence of perfect numbers. The only possible prime numbers you can get in this way, 2 to the L minus 1, sort of start like this exponent itself also has to be a prime number. Okay, but that's not sufficient. So you can just sort of start computing these Mersenne. So a number of the form 2 to the L minus 1 is called a Mersenne number. And if it's prime, it's called a Mersenne prime. And you can just start computing those when the exponent L is prime. And for a little bit, you'll end up with sort of Mersenne primes. But when you plug in L is equal to 11, you'll get 2 to the 11 minus 1. So that's 2047. And that is not a prime number. That factors as 23 times 89. Okay. It's a necessary condition if 2 to the L minus 1 is prime. So a necessary condition for Mersenne prime is that you take the exponent to be prime, but it's not a sufficient condition. But there's a really amazing thing that happens with Mersenne primes, is that for these numbers of the form 2 to the L minus 1, there's a really efficient way to check whether this is a prime number or not. So you'll remember before earlier in the class, I've made a big deal about how factoring numbers is hard. I mean, sort of the only like general, sort of some of the obvious algorithm for factoring a general number is you just sort of start dividing it by everything that's sort of less than its square root, and it's going to be prime if you never get something that divides it properly going through those. And somehow you don't actually do much better than that. Like, we don't know a way to factor things or check if things are prime that's much more efficient than that in general. But and this sort of still leaves open the possibility that sort of for numbers of a certain shape, like, or a certain form, like sort of 2 to the power minus 1, that for such a number, maybe there could be an efficient way to check whether that kind of thing is prime. And in this case, there's something called the Lucas-Lehmer test, which reduces sort of checking whether 2 to the L minus 1 is prime to just sort of doing a single division. So instead of having to divide by sort of every number less than sort of the square root of this, you just have to do a single division, sort of using some auxiliary numbers, though. They can get very big. Okay, but this is a very special thing, and we'll explore this a little bit on the worksheet, and also after spring break again. But good, and this is actually how the largest prime number we know was discovered. And if you want to find really, really big prime numbers, you need to sort of look at numbers of a special form where you have a good way to tell whether they're prime, like this Lucas-Lehmer test. And so people have done that sort of by running computers for a very long time. And this right here, 2 to the 82,589,983 minus 1, this is the largest prime number that we know. In the sense that we know there are larger prime numbers, but we don't know any specific number that's larger than this, which we can say for certain is prime. So this is sort of somehow the largest number that we're able to say for certain is prime. And this is a very big number. It has almost 25 million digits. So it would take you sort of quite a while to even like write this down and sort of try dividing it by one thing. More than the rest of your life, probably. Okay, good. So that's just a little bit about Mersenne primes. Let's go back to even perfect numbers to finish up the lecture for today. The question we should be left with is, how do you prove this Euler's theorem? So Euler's theorem was this characterization of even perfect numbers in terms of sort of this thing built out of these Mersenne primes. So how would you prove this? So the main idea is you should look at this function sigma of n. So this is the function that takes a number, takes it in a positive integer n, and spits out the sum of all the divisors of n. So here I'm allowing n itself. So g sigma of 6 would be 1 plus 2 plus 3, and then I'm allowing I'm not just taking proper divisors, so I also allow 6 to be in that sum. This is 12. Okay. Well, 12 is 2 times 6, and 6 was a perfect number, and this is sort of no coincidence. We sort of look at this function, then n is perfect if and only if sigma of n is equal to 2n. And the point here is sort of being perfect meant if you added up all the proper divisors, you got n, but then you're also sort of adding n itself. So like here, this is these things, because 6 was perfect, 1, 2, and 3 added up to give 6, but then we also add another copy of 6 just because we're not something, because we also allow n itself in this definition of sigma. Okay, so we'll see how this is useful in a second. Let me just first verify let's first verify that these numbers in Euler's theorem really are perfect numbers. So let's suppose we have a Mersenne prime, writing m sub l, and so 2 to the l minus 1 is m sub l, and we're assuming that's prime. And then we're looking at the number n, which is 2 to the l minus 1 times m sub l. So this is the thing that Euler's theorem says is supposed to be perfect. Well, then the divisors of n I can just write them out. It's pretty easy because there are only two prime factors. I mean, there's 2 as a prime factor, and then this m sub l is a prime factor that divides it exactly once. So all of the divisors are just given by sort of some power of 2 less than l minus 1 times some power of this guy, m sub l, that's either 0 or 1. So like I get 1 and ml, and I get 2 and 2 times ml, and I get sort of maybe 4 and 4 times ml, and so on, all the way up to 2 to the l minus 1 and 2 to the l minus 1 times m sub l. Okay, and so if I add all those up, then I get just 1 plus 2 all the way up to 2 to the l minus 1 times 1 plus ml. So this sort of comes from like grouping the terms like this. Okay, right, and well, it's not so hard to see that this, I'm just using maybe what you know about geometric series from calculus, that this first part gives me 2 to the L minus 1. So if I sum up sort of powers of 2, I get the next power of 2 minus 1. And then let me just plug in what m sub l was. Well, m sub l was 2 to the L minus 1. So here I get so 2 to the L minus 1 times 2 to the L, which let's rearrange those terms. That's 2 to the 2 times 2 to the L minus 1 times 2 to the L minus 1, which is 2 times n. So this part was m sub l, and then this was the definition of n, was 2 to the L minus 1 times m sub l. And that's exactly what we needed to check to see that n was a perfect number. We needed to check sigma of n was 2 times n. Oops. Okay. Good. So that gives the easy direction of Euler's theorem. I mean, this fact was actually known to the ancient Greeks, that if you wrote down a number like this, that gave you a perfect number. So what's more interesting is how you can use properties of the sigma function to show the other direction, to show that if you have an even perfect number, then it is of this specific form. Okay, and so there you're going to use the following 2 key properties, which are just like sort of the properties of the Euler's phi function. So first, if you look at a prime power, so if I look at sigma of p to the k, I'm just all dividing up all of the divisors of that prime power, then this has a very simple form. It's just 1 plus p all the way up plus p squared all the way up to p to the k, which sort of using the summation formula for geometric progressions, I can write as p to the k plus 1 minus 1 over p minus 1. Good, so just like Euler's phi function, there's a simple expression for it when you evaluate a prime power. And then it's not too hard to see also that sigma of a times b is equal to sigma of a times sigma b if the GCD of a and b is equal to 1. And again, this is sort of just like for Euler's phi function, although in this case, it's actually even easier to check. It's basically like what was going on up here in this example. Here, like when we looked at n equals 2 to the L minus 1 times ml, we computed sigma of that. Well, when we arranged the divisors, sort of all of those look like some power of 2 times sort of up to sort of the maximum power of 2 times some power of ml, sort of up to the maximum power there. And then we just multiply those together. But like this term is sort of sigma of 2 to the L minus 1, and this term is sigma of m sub l. And we're just multiplying them. Okay, so if you think that through a little bit further, you'll see that this statement is not so hard to justify. Okay, so let's sort of sketch how to do this argument. I'm not going to do the whole thing, but I'll do part of it, and then I'll sort of tell you where to look for the rest. So let's just see what happens if we sort of say we have an even perfect number. And well, okay, if n is even, I can write it as sort of 2 to the some positive power times an odd number. And let me go ahead and somehow I ultimately want it to look like this, like 2 to the L minus 1 times m sub L. So let me start by sort of calling that even power to the L minus 1. So I'm taking some L larger than or equal to 2. But this is sort of just notation to match, because I want to sort of end up matching what I had before. Okay, and well, now let's apply sigma. So sigma of n, so the sum of the divisors. Well, because 2 to the L minus 1 and R have GCD 1, because R is an odd number, this is sigma of 2 to the L minus 1 times sigma of R. Good, and then this is equal to uh, 2 to the L minus 1. So if I sort of plug in this formula for sigma of 2 to the power, I just get 2 to the L minus 1 times sigma of R. But on the other hand, this left-hand side, sigma of n, so on the right-hand side, I've just expanded the first term. Then on the left-hand side, I'm going to use that n is a perfect number to write this as 2 times n. Okay. And then let me sort of write out this part. So n was 2 to the L minus 1 times R. So this is sort of 2 to the L times R is equal to 2 to the L minus 1 times sigma of R. Okay. So in particular, yes, let me just write here. Here, this left-hand side of how I added equality was just because n is perfect. So n is perfect is equivalent to sigma of n is equal to 2n. So great. In particular, from this last equality, I get that 2 to the L minus 1 divides 2 to the L times R. But this number is odd, so it can't sort of divide this part coming from the 2 to the L, so it has to divide R. So 2 to the L minus 1 divides R. And so I can rewrite, so this is actually pretty good, because now I can rewrite n, which is 2 to the L minus 1 times R, as 2 to the L minus 1 times 2 to the L minus 1 times some other number s. Okay, and then I just need to show, so it remains to show that s is equal to 1, and 2 to the L minus 1 is prime. Okay, so I sort of got the part I want. Now I just need to sort of check that I get that s has to be equal to 1, and that this part should be prime. But sort of somehow I'm already doing a lot better having gone down to here, because sort of now, like, I know it sort of can be written in sort of a nice form that looks like what I want. I just have to check something about 2 numbers appearing in that form. Good, and so you can do this using basically, there's just one more clever argument you have to write down. It's a little bit, I think it's a little bit too hard to follow if I try to write it down here, so I'm not going to, but you won't have any problem reading it if you look it up in the textbook. So the rest of the argument, the last part of the argument sort of is on page 61 in the book, and it's just sort of one more clever estimate / argument that you have to just trace through a little bit carefully. But again, sort of you'll be able to do that if you're interested in. Okay, but let me stop here and I will see you all in class. Thank you.